Welcome to the Crazy Hat Chemist. Today we are going to do the Introduction to Stoichiometry Worksheet 1 and all its solutions. Um, Today's video is not a lecture, but a paper and pencil explanation of a problem set in stoichiometry. And before starting this problem set, I'm going to assume that you have done the following. You have either understood the concepts or watched my videos in Honors Chemistry 1, that's the chemical nomenclature collection. Honors Chemistry 8, that is chemical reactions collection. And Honors Chemistry 9, the stoichiometry collection. I'm also going to assume that this flow chart here makes sense to you, and you also have a periodic table. So before we get started on the first problem, let's just make sure that we understand what this flow chart is all about. So here we go. On the far left-hand side, we have mass. That would be in grams. We have right here 1 mole. And then right here, we have molecules. And right here on the far right-hand side, we have atoms. To go from mass to moles, we're going to be using the molar mass. The molar mass is calculated using a periodic table. And today we're going to be using the periodic table just like this one right here. So it's very specific. So make sure that you use this periodic table. Otherwise, your molar masses and rounding and significant figures will be incorrect. So it's the SAT subject test, old periodic table. So going from mass to moles, you're going to have to use this conversion of molar mass. That will equal 1 mole. Going from moles to molecules, you're going to be using Avogadro's number, and we're going to be using this number, 6.022 times 10 to the 23rd. That is Avogadro's number. Going from molecules to atoms, it will be 1 molecule and a counted number of atoms. And so if you look here at the very top here, it says 1 molecule is equal to, of H2O, is equal to how many atoms of hydrogen? Well, how many atoms of hydrogen do you see? There are 2. So this would be 2 right there like that. And 1 molecule of H2O has how many atoms of oxygen? That would be 1, and that would be 1 right there like that. And the total number of atoms is the sum of the 2 and the 1. That's 3. Let's give another one a try. And this is 1 molecule of ammonium sulfate has how many atoms of nitrogen? And so I'm going to distribute this 2 over what's inside the parentheses. So that will be a 2. How many atoms of hydrogen? And that is distributing this 2 here. And that's 2 times 4. That is 8. How many atoms of sulfur? That's 1. How many atoms of oxygen? That's 4. And then the total number of atoms is 2 plus 8 plus 4 plus 1 plus 4. That's a total of 15. Okay. And then we can also go in the reverse direction. So atoms to molecules, I'm going to be using the conversion of 1 molecule for a counted number of atoms. So that is 1 molecule and a counted number of atoms, depending upon the formula and the number of atoms that you're looking for, if they are the total number of atoms or a specific number and type of atoms. Going from molecules to moles, we're going to be using Avogadro's number for molecules, that's right here, and 1 mole. Going from moles to mass, we're going to use 1 mole and the molar mass in grams to get mass. And then one more thing here, and that is going down on this flow chart, and that is 1 mole is equal to 22.414 liters of any gas at STP, that's standard temperature and pressure. So I can go from moles of any gas to volume of any gas at standard temperature and pressure. Okay, so I'm going to assume that you understand this flow chart. The one thing that we are not doing in this video here today is using a mole ratio, and that's going up on this. So we won't be using that for this specific worksheet today. We'll be going across, back and forth, and up and down, as well as some other kinds of concepts built within this first introductory stoichiometry section. So I'm going to pull this off to the side. and put back on here the periodic table that we'll be using. So just making sure that this is the periodic table that we'll be using for calculating the molar mass of all the formulas here. All right, fantastic. So pulling both of these aside, I'll refer back to those in a little bit. So what we can do is get started on the first problem here. This is the Introduction to Stoichiometry Worksheet 1. And here's our first problem here. So let's zoom in on this a little bit and get squared away. All right, fantastic. All right, so it says how many moles are in 0.18 grams of calcium chloride? So the first thing that we're going to do is we are going to use this concept of NUF, that is, and I'll write this right up above here, that is NUF. And that what that means is a number, units, formula. And you're going to be using NUF every single step of the way as much as you possibly can. So number, units, formula. Make sure that you're using a number, units, and formula for every single step along the way, and you won't go wrong. I guarantee you, if you do it this way, you will be much better off and you'll get the right answer. If you take shortcuts, then more than likely you'll get the wrong answer. That's just how this game works of stoichiometry or dimensional analysis. So on this first problem, we're going to find our number that is right here, 0.18, and then the units are grams, and then the formula is the composite of calcium chloride. So we're going to figure out what that is. So we're going to first write out the number, that's 0.18, then the units of grams, and then we're going to come up with the correct formula for calcium nitrate. Calcium chloride. And so this is actually a periodic trend formula. So calcium is right here, and that is a 2 plus. And so that's a periodic trend. And then chloride, that's a halide ion, that's right there, and that's a 1 minus. So I'm going to take those two together, and I'm going to get my formula. So I'm going to write that right over here off to the side. That's calcium, 2 plus, chloride, 1 minus. I'm going to take the absolute value of these two right here, take these numbers, flip them, and bring them down. I call it taking the bull by the horns, flipping it and bringing it down. And so I got Ca, there's an imaginary 1 and a Cl and a 2. So that's my formula for calcium chloride. I'm going to incorporate that in this. So number, units, and the formula CaCl2. Okay? Fantastic. And then what we're going to do is we have started off with our number, units, formula, and then we're going to go from there, and then we're going to draw this monorail. Okay. So we have our number, units, formula. We've used that, and then we're going to figure out what we're solving for. And we're solving for moles in this problem. So I'm going to bring back my flow chart. And what I have to begin with on this problem is mass, and I'm going to go to moles. So what do I need to go from mass to moles is the molar mass. That's kind of my ticket to cross this bridge here. There's a bridge from mass to moles or moles to mass, and that bridge is the molar mass. I need that ticket of molar mass. So I am going to, in order to do this, what we need to do is take the units that are here, which is grams, and I'm going to place those same units here down here in the denominator. That allows me to cancel out the units. Furthermore, I'm going to take the formula here, CaCl2, and place this down here, CaCl2, just like that. And then I'm going to look at my flow chart again. I'm going from mass to moles. So this tells me what are the units in the numerator. I'm going from mass to moles. The units in the numerator are going to be moles. The numeric value for it is going to be a 1. So that's going to be moles. And that's CaCl2, and the numeric value is 1 in front of the mole. Then what we need to do is we need to calculate what's called the molar mass. Again, that's my ticket, the molar mass. I need to calculate the molar mass of calcium chloride. And so what we're going to be using here is the mass of calcium, that's 40.08 times 1, because there's 1 calcium. and then 35.453 times 2. And then I'm going to round this number to the least number of decimal places. Chlorine has 3, calcium has 2. So I'm going to round that number, calcium chloride, that I get in my calculator to 2 decimal places. And that will be 110.99. And you should see that the reason we do everything on this problem here, the way we do it, is we are going to cancel out our units and formula. We're going to cancel out our units and formula. And what we are left are the units and the formula of what we want. Okay. And so we're going to put a little equal sign right over here. And then we're just going to do the math. So we're going to plug this into our calculator. We're going to say 0.18 times 1 divided by 110.99. Okay. And in order to get the correct numeric value here, we're going to round this correctly. So leading zeros do not count. All non-zero integers count. So the number of significant figures here is 2 significant figures. This is an infinite number of significant figures for this one, because this is a definition that is 1 mole equals the molar mass. The molar mass is a calculated value from our periodic table and has 1, 2, 3, 4, 5 significant figures. This is a captive zero, so that counts 5 significant figures. Therefore, my answer that is rounded correctly will have the least number of significant figures, since this is multiplication and division, and that's 2 significant figures in my correctly rounded answer. So my correctly rounded answer is 1.6 times 10 to the negative 3. That's my numeric value, and I'm going to have the correct units, which is moles, and then the correct formula, CaCl2. And so this is my correct numeric value with the units and the formula. And again, NUF, number, units, formula. Awesome. Just did the first problem, very first baby step. So hopefully that worked out okay for you. And let's move on to the next one. Okay, so the next one is right below here, and it says determine the number of grams in 1.65 moles of Nicholas hydroxide. So this problem is almost effectively the reverse of the problem that we just did here. Okay, and we're not going to do anything different than what we did, and that is we're going to start off with the same thing. We're going to have a number, units, and then the formula of this composite of Nicholas hydroxide. And then we're going to ask ourselves, well, what are we solving for? We're going to solve for grams. So we're going to start off with a number. That's 1.65, and then the units are moles, that's MOL, and then it's Nicholas hydroxide. So Nicholas is nickel with a 2+ charge. Hydroxide is a polyatomic ion. That's a 1-. I'm going to take the absolute value of these two numbers, flip the numbers. That's NiOH, and this requires a parentheses and a 2 outside. That's Nicholas hydroxide. So hopefully that worked out for you. So that's NiOH and a 2 outside there. And again, we're doing the same thing. We're going to do a monorail, okay? And the whole process here is canceling out units and formula. So that's the reason why if there's moles here, we're going to have moles down here in the denominator. And then whatever this formula is here, NiOH parentheses and a 2, NiOH parentheses and a 2. And then we're going to look on our flow chart right over here. So our flow chart, we have moles to mass, and the number in front of the mole is a 1. And the conversion between moles and mass is the molar mass. So I need to calculate the molar mass. So it's going to be 1 mole in front of the mole, and then grams for the Nicholas hydroxide, just like this. And now we need to calculate the molar mass of Nicholas hydroxide. So we need to get our periodic table again. And we are going to find out the molar mass for nickel. There's 1 of those in this formula. And then hydroxide is 2 oxygens and 1 hydrogen. Excuse me, 2 hydrogens. So, excuse me, let's try that again. 1 nickel, 2 oxygens, and 2 hydrogens. So we're going to sum up all those numbers and then round it to the least number of decimal places, which is 2. And so that molar mass will be 92. Let me write that again, 92.71. That is the molar mass for Nicholas hydroxide. And again, the reason we're doing this dimensional analysis, stoichiometry for chemists, is we're going to cancel out our units and formula, and then we're going to get a numeric value for this. So let me zoom on out just a little bit so we can get a little bit more involved in here. And so we are going to round this numeric value after all this is said and done to the correct number of significant figures. This is 3 significant figures. This is an infinite number of significant figures. This is 4 significant figures. The least number of significant figures I have here is 3. My answer will be rounded to 3 significant figures. My number is 153. That's grams of NiOH2. So again, I have number units formula, and it's rounded correctly. So I'll let you figure out what your calculator value is, but that is the correctly rounded number. All right. Let's move on to that next problem here. And the next one here is number 3. And number 3, it says we have 9.5 times 10 to the 20 atoms of barium hydride. Is equivalent to how many grams? So I'm going to figure out grams, and I have atoms. So what we're going to do is we're going to use our flow chart, and I'm going to zoom on out here so you can see this entirely. Okay, and so we are starting with atoms, then we need to go to molecules, and then we need to go to moles, and then we need to go to mass. There is no direct flight from atoms to mass. There is no direct flight. So you actually have to do each one of these steps individually. So I'm going to first go from atoms to molecules, then molecules to moles, and then moles to mass. All right, so let's start off with a number units formula. That's 9.5 times 10 to the 20, and it's atoms. And then it's barium hydride. So let me zoom back in on here on this problem. There's the 9.5 times 10 to the 20 atoms, and then barium. Barium is right here. That's a 2+, and hydrogen is a hydride when it's combined with either a group 1 or a group 2. So it's Ba2+, H, and a 1-. Take the bull by the horns. That's the absolute value of these. Flip the numbers, bring it down. You get BaH2. That's barium hydride. Okay. Fantastic. So now what we're going to do is do our little monorail here and see how far we can go with this. All right. So I see that atoms are down here. Sorry, atoms are in the numerator here. Then I will have atoms down here in the denominator. Atoms. And then BaH2, the same formula. And then if I look at my flow chart, I'm going from atoms to molecules. So this tells me what are the units in the numerator. So I'm going to have molecules, MOLEC, and of the same formula, BaH2. And then there's my line. So now if I look at this from atoms to molecules, it's 1 molecule. Do you see that right there? It's 1 molecule and a counting number of atoms. Effectively, that's what I did right up here. This whole section over here, that's what I kind of covered over there already. So it's going to be 1 molecule and then a counting number of atoms. So we're going to look in this formula. There's 1 barium and 2 hydrogens. So that's 1 plus 2. That's a total of 3 atoms. And we are doing this in this correct sequence so that the atoms of barium hydride cancel out. So hopefully you see that. The next step is to take molecules down here in the denominator. That's MOLEC and BaH2, just like that. And I'm going to go from molecules to the next thing. So I'm actually in this section. I'm starting with molecules, and I'm going to go to moles. When I use molecules, it's going to be Avogadro's number when converting to moles, and the number in front of the mole is a 1. This tells me the numerator units and number. Numerator units, mole, and the number, and the same formula, BaH2. Okay, and then the number in front of molecules is Avogadro's number. That's 6.022 times 10 to the 23rd. Okay, again, on this section, the molecules of BaH2 will cancel out. I'm not quite done yet because I'm trying to solve for grams. So whatever these units are here in the numerator, you must have the same units in the denominator of the next term, and then BaH2. And so now I'm going to go from moles to mass, and I'm going to be using the molar mass, and the number in front of the mole is a 1. So it's a 1, and then it's grams of BaH2, just like that. And now I'm going to look at my periodic table. I'm going to find barium, that's molar mass right there of 137.33. I'm going to multiply that by 1, and then hydrogen 1.0079 times 2. And then I get a molar mass with 2 decimal places. So that's 139.35. And then I should see that my units of moles of barium hydride cancels out. And then I'm looking at significant figures. This has 2 significant figures. This is a counting number of atoms. That's infinite. This is a definition. 1 molecule equals a counting number. That's a infinite. This is definition, infinite. This has 4 significant figures. This is a definition, infinite, and this has 5 significant figures. So the fewest number of significant figures I have on this problem is 2. So I'm going to take this number times 1 times 1 times 139.35 divided by 3 divided by Avogadro's number divided by 1. And then when I do that and round it correctly, I'm going to get 7.3 times 10 to the negative 2 grams of BaH2. And that is my rounded numeric value right there. 7.3 times 10 negative 2 grams of BaH2. Right. Pretty happy with that. So let's cruise on to the next problem here. Next problem, it says how many atoms are in 2.3 moles of fluorine? So I am looking for atoms. So I'm going to start off with 2.3 moles of fluorine. So 2.3 moles. And then fluorine is one of the diatomics. So I'm hoping that you do remember your diatomics. And here are the diatomics. That is nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Those are the diatomics. So they have formulas of like X2, N2, O2, F2, Cl2, Br2, I2, and H2. Those are the diatomics. So this is fluorine, so that's F2, just like that. And we're going to have our monorail. So it says we have 2.3 moles of this, and we want to go to what atoms? So I'm going to go back to my flow chart, and hopefully that helps us out. We are going to start with moles, and we are going to go all the way to atoms. That's on the far right-hand side of our scale here. So going to go from moles to molecules and to atoms. There is no direct route, so you have to go in sequence. So we're going to go from moles to molecules. What's the number in front of the mole? 1. What are the units in the numerator? Molecules. So moles of F2, and then the units in the numerator are going to be molecules, MOLEC, and F2. The numeric values for these now are based on this flowchart. And the number in front of the mole is a 1, and the number in front of the molecules is Avogadro's number. And so we're going to have 1 in front of the mole, and then Avogadro's number, 6.022 times 10 to the 23rd. And this enables us to cancel out the moles of F2. Now we need to do the next step, and we're trying to get to atoms. So we're going to say we have molecules here in the numerator. We will have molecules here in the denominator, and that's F2. And then we are going to go from molecules to atoms. The number of molecules is 1, and I'm going to count the number of atoms. So the number in front of the molecules is a 1, and then I'm going to have atoms, and it is going to be fluorine, and that would be 2 atoms. Why 2? Because I'm counting 1, 2. Okay, perfect. And so this enables us to cancel out molecules of F2, just like that. And now we're going to look at significant figures. This has 2 significant figures in this numerator. This has 4 significant figures here. This has infinite number of significant figures because I counted it. Infinite number of significant definition. Infinite number of significant figures definition. So the fewest number of significant figures in this problem is 2. So I'm going to take 2.3 times Avogadro's number times 2 divided by 1. So that will be 2.8 times 10 to the 24 atoms of fluorine. Notice that it's not F2, okay? All right, cool. And now we are done with number 4. We are up to number 5. All right, let's stay alive with number 5. Okay, so number 5, we're going to go from grams of ammonium nitrite. That's an ite. How many molecules are in this? So we're going to go from grams, and then we're going to move on to the next step there, but eventually end with molecules. So we're going to start off with a number, units, and formula. So that's 1.260 grams of ammonium nitrite. So ammonium is NH41 plus, nitrite is NO NO2, like that. Okay, and so then we're going to do this just like this. Boom, boom, boom. Perfect. And I don't think I previously calculated this molar mass, so we're going to calculate this molar mass. So how many nitrogens are in this formula? There are 2. And the molar mass for nitrogen is 14.007. So I'm going to multiply that by 2. Then there are hydrogens, of which there are 4 in this formula. And so that is 1.0079 times 4. And then there are 2 oxygens, and oxygen is 16. So 16 times 2, and then we are going to get the molar mass of 64. I'll write that down in just a moment. So we're going to have grams down here of NH4NO2. And that molar mass is going to be rounded to 2 decimal places because the oxygen has 2 decimal places, the nitrogen has 3, and the hydrogen has 4. So we're going to go with the fewest number of decimal places. So that's 64.05, rounded correctly. Okay, and now what we're going to do is we're going to look at our flow chart, and we're going from mass to molecules eventually. So we're going to go from mass to moles. That's the only thing we can do. So in the numerator term is going to be moles. So this will be mole. Same formula, NH4NO2. And then the numeric value in front of the mole, hopefully you're getting that, is an absolute 1. So that's a 1. This enables me to cancel out units and formula just like thus, okay? And then let's see here, the next step here is that we want to get to molecules. So therefore, we need to have the units of moles down here, and that's NH4NO2. That allows me to cancel out moles of NH4NO2, just like that. Okay, and in our flow chart, where are we? We are going from moles to molecules. So we have moles in the denominator, as you can see, and we're going to go from to molecules. So therefore, molecules is in my numerator term, as well as those same formula, NH4NO2, like that. And now I need to figure out the numbers. The number in front of the mole is a 1. The number in front of molecules is Avogadro's number. So number in front of the mole is a 1, and number in front of the molecules is Avogadro's number, 6.022 times 10 to the 23rd. And then I'm going to be left with molecules. So in order to plug this into your calculator, you're going to take this number times 1 times Avogadro's number divided by 64.05 divided by 1. Number of significant figures. This has 4 significant figures. Trailing zeros count when there's a decimal. This is infinite number of significant figures. This is 4 significant figures. 4 significant figures and infinite. So it looks like the fewest number of significant figures I have on this problem is 4. So you're going to plug all this into your calculator and you're going to get the following rounded number, 1.185 times 10 to the 22 molecules of NH4NO2. Cool. So hopefully you see that just fine. 1.185 times 10 to the 22 molecules. All right. So we've done number 5. That's looking pretty good for us. We're going to move on to the next problem here, but just a little advertisement break here, if you will. You are watching the Crazy Hat Chemist. And if you're liking how I'm going over these problems, please give me a thumbs up and please subscribe to my YouTube channel. I would greatly appreciate that. All right. So we're going to get rid of this page over here and we're going to go to the next page. So let's get this on the table here. Okay, so we have grams of sulfuric acid and it says how many atoms of oxygen in this. Okay, so we're going to start off with number units in a formula. So that's 3.501. And that's grams of sulfuric acid. So sulfuric, it doesn't say hydro, so it's not a binary nonmetal acid, it's a polyatomic ion acid. So we're going to have H2SO4. Okay, we're going to continue this here. We have grams of H2SO4 in the numerator, therefore we must have grams of H2SO4 in the denominator. Okay, and I'm going to pull out a new flow chart here. So we got grams, which is a mass, and we're going to go from grams to moles. This tells me the units in the numerator, which is moles. So this is going to be moles of the same formula, H2SO4. And then now what we need to do is get the numeric values for this. The number in front of the mole is a 1. The number in front of the grams is going to be the molar mass. So I need to calculate the molar mass for sulfuric acid. This is 1 in front of the mole. And the molar mass right here is going to be grams. And so I'm going to look on my periodic table. I am going to find hydrogen. There's the molar mass for hydrogen. I'm going to find sulfur. By the way, there's 2 hydrogens in that. Then for sulfur, I'm going to take this molar mass for sulfur, multiply it by 1, and then multiply the molar mass of oxygen by 4. And that will give me the molar mass. And I'm going to round that to 2 decimal places. So that'll be 98.08. Again, your units and formula cancel out just like that. I'm not done, so I need to keep on going on this problem here. And so I'm going to keep on with my little monorail here. Whatever these units are, those same units go in the denominator of the next term. That's moles and same formula, H2SO4. Okay, and then in the numerator, I'm ultimately trying to get to atoms. So I'm going to start off at moles, and I'm going to go to molecules, and eventually over here on the right-hand side to atoms. But I first need to do this one, from moles to molecules. Again, remember the number in front of the mole is a 1. Okay, so the number in front of the mole is a 1, and then I'm going to go molecules of H2SO4, and then draw a line. And what's the number in front of the molecule? Well, it's Avogadro's number when I'm going from moles to molecules or molecules to moles. So Avogadro's number here, 6.022 times 10 to the 23rd. That allows me to cancel out moles of H2SO4. Looking good. I like it. Okay, I'm not done because I need to go to atoms. So molecules are right down here. So this is molecules of H2SO4, just right on the edge here. So I like playing on the edge. This will allow us to cancel out molecules of H2SO4. So I'm at molecules and I'm going to atoms. So it's 1 molecule for a counted number of atoms. Okay, so 1 molecule for a counted number of atoms. So let's reread the question and make sure that we understand what we are asked to solve for. And it says, how many atoms of what? Not total atoms, but atoms of oxygens. So How many atoms of oxygen here? There's 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. I'm looking for the atoms of oxygen. So there are 4 atoms of oxygen. Okay. All right. So now what we're going to do is look at our significant figures. We have 4 significant figures here. We have 4 significant figures here. Infinite, infinite, 4 significant figures. Infinite number of significant figures because we counted it, infinite number of significant figures with a definition. And so the fewest number of significant figures on this problem is 4. So we're going to take this number times 1 times Avogadro's number times 4 divided by 1 divided by 1 divided by the molar mass of 98.08. And then that will have 4 significant figures. So we are going to have our correctly rounded answer as 8.598 times 10 to the 22 atoms of oxygen. Perfect. Okay. All right, so now what are we going to do? We're going to do the next problem. And the next problem is a percent composition by mass of ferric iodate. So the first thing that we need to do is we need to get the formula for ferric iodate. And so I'll move this up just a little bit. Hopefully I have enough space to do this one. Ferric is Fe3 plus. Iodate is IO3 with a 1 minus. So the correct formula for ferric iodate is Fe parentheses IO3 with a 3 outside there like that. Okay. And when we are getting percent composition, we are getting the percent of each element within that formula. So how many irons? 1. How many iodines? 3. How many oxygens? 9. So I'm just going to get 3 percentages. Okay, so in order to complete this problem, what we need to do is get the molar mass of ferric iodate. So I'm going to look up on my periodic table, look up iron, multiply it by 1, iodine, multiply it by 3, oxygen, multiply it by 9, and then I'm going to round that to the fewest number of decimal places. So just so happens, let's see, do we have a periodic table rolling up here? Oh, we do. Perfect. So for iron, here is iron's molar mass of 55.85. I'm going to multiply that by 1. Iodine is right here at 126.91. I'm going to multiply that by 3. And then oxygen is right here at 16.00. I'm going to multiply that by 9. And then I'm going to have 2 decimal places in my final rounded answer for ferric iodate. So that value for the molar mass of this is 580.58 grams per mole. That's the molar mass for ferric iodate. All right, so what we're going to do is get the molar mass for iron. That's 55.85. And we're going to multiply this by 1. Why? Because there's only 1 iron in this formula, and we're going to divide by the total molar mass of the compound. That's 580.58. And then we're going to multiply by 100 because we want a percentage. We're going to round this to the fewest number of significant figures, which is 4 in this case. And so this is going to be 9.620% of iron, Fe. So I have number, units, and a formula. My units in this case are percent. Okay, and then the next one I'm going to do is the iodine. The iodine's molar mass, I'll do this in a different color so you can distinguish this here, hopefully. The iodine's molar mass is 126.91, and there are 3 iodines in this, so I'm going to multiply this by 3. And then I'm going to divide this by 580.58, multiply that by 100, and I'm going to get the percent of iodine in this formula of ferric iodate, and this is 65.578% iodine. And this one has been rounded to 5 significant figures. And then the percent of oxygen here is the molar mass for oxygen is 16.00. There are 9 of them. And I'm going to divide by the molar mass of the entire compound. That's 580.58. I'm going to multiply by 100. And then I'm going to get the rounded answer with 4 significant figures of 24.80% oxygen. Fantastic. And if this is correct, then what you should be able to do is sum up this number, sum up this number, and sum up this number, and they should be very closely approximating 100%. That should be your check on this problem to see if you got it correct. And if you don't check that, that is totally bad on you. So make sure you check that. All right. So our next one, cruising on up here, is right here. We're going to calculate the liters of nitrogen dioxide gas at STP if you have 2.18 grams of the compound. All right, so we're going to start off with number, units, and formula. And the number is 2.18. The units are grams. And the formula for nitrogen dioxide, this is a binary covalent compound, and it uses prefix naming, therefore the di. There's 1 nitrogen and there are 2 oxygens. So that's nitrogen dioxide. Okay, and then we're going to do our little monorail here. We're going to stretch that out. So we have grams and we're solving for liters at STP. So let's look on our map and our map and figure out where we are. We have a grams, which is a mass, and we want a volume, and that's liters. There is no direct flight from mass to volume, so we're going to have to go from mass to moles, and then from moles to volume. So mass to moles. Okay, so therefore grams are in the numerator here, grams will be in the denominator here of NO2, and then in the numerator, I will have moles. Mass to moles. This tells me my units in the numerator and the number is a 1. So this is 1 mole of NO2. And then this number in the denominator is the molar mass for nitrogen dioxide. And so we're going to take nitrogen, and that's right here. 14.007 times 1, oxygen 16.00 times 2, and then round that to 2 decimal places, because that's the fewest number of decimal places. And that number will be 46.01 grams. I'm canceling out the grams of NO2. Perfect. Now, moles of NO2 are in the numerator, therefore moles of NO2 must go in the denominator. And if we look at our flow chart, the numeric value of that in front of the mole is a 1. Perfect. So this is a 1 right there. All right, now this will enable us to cancel out moles of NO2. And again, we are trying to solve for liters, which is a volume. So I am going to go from moles to volume, and I can only do this if it's at STP, and that is 1 mole is equal to 22.414 liters. 1 mole is equal to liters, and that's 22.414, and that's NO2. Perfect. So now we're looking at significant figures. This has 3 significant figures. This has infinite number of significant figures, 4 significant figures, 5 significant figures, and infinite number of significant figures. So it looks like the fewest number of significant figures I have on here is 3 significant figures. So I'm going to get my calculator number and then round it to 3 significant figures. That'll be 1.06 liters of NO2. Circle that. And that should be your answer. Cool. Okay, here we go. We're going to keep on going. Not too bad so far. Hopefully I'm going slow enough for you to catch on each of these steps so that you get this stoichiometry. It's really important that you truly focus in on this stuff and get it to begin with. Okay. Next one, we have 0.066967 moles of plumbic chromate. Oh my gosh, plumbic, Pb4 plus chromate, polyatomic ion, CrO4, and a 2 minus like that. So that's plumbic chromate. I'm going to take the absolute value of these two charged values, take the bull by the horn, flip it, bring it down, and then you're going to see the formula that I write down for this. All right. So what we're going to do is we're going to start off with 0.0967, and that is moles, MOL, of plumbic chromate. That's PbCrO4 and 82. It's going to be a long one just because the formula is quite elaborate. Okay, so we are going to calculate the number of atoms, in fact, the total number of atoms. Okay, and so we're going to cruise on over here and figure out where are we on our flow chart. So where are we? We are at moles and we want to go to atoms. So that is far off to the right here, off to the side on the right. So we're going to go from moles to molecules. So whatever these units are, these are moles. And of the same formula, PbCrO4 and a 2. And I'm going to go from moles. I'm going to go from moles to molecules. So molecules is my numerator units, MOLEC, and the same formula, PbCrO4, 2. Now I'm going to figure out what the numeric values are for the moles and the molecules. So the moles is a 1. The molecules is Avogadro's number. Moles is a 1. Molecules, Avogadro's number, 6.022 times 10 to the 23rd. Okay, this enables me to cancel out moles of plumbic chromate. Now, molecules is in the numerator here, therefore molecules needs to go in the denominator. Same formula, PbCrO4 and a 2. And then I'm going to go from molecules to what? To atoms. So I'm going to go from molecules to atoms. So molecules, atoms. Atoms tells me, so from molecules to atoms, this tells me the numerator term units. So that would be atoms. So these are atoms. And it says atoms total. So we could just say atoms in PbCrO4 and a 2. Okay. And so what are the numeric values for this? So it's 1 molecule and a counted number of atoms. So it's 1 molecule and a counted number of atoms. So I'm going to look at this and I'm going to go, okay, there's 1 lead, there's 2 chromiums, and then there's 8 oxygens. So 8 plus 2, okay, that's 10, plus 1, that's 11. So this is 11. Okay. Perfect. Molecules of PbCrO4, 2 cancels out. And I'm looking at significant figures. Leading zeros do not count for significant figures, but they are important for placeholders. So this is 3 significant figures. This is 4 significant figures. This is an infinite number of significant figures. Infinite because it's a definition. Infinite because I'm counting. So I'm going to have 3 significant figures in my rounded answer. So I'm going to plug all this into my calculator. This number times Avogadro's number times 11 divided by 1. So that makes it easy, relatively. And so I'm going to get the rounded answer of 6.41 times 10 to the 23rd atoms total in PbCrO4, 2. Perfect. All right. I like that. You got that one done. All right, let's move on to number 10. And we are almost halfway done with this worksheet, by the way. I think there are a total of 20 problems. So yeah, we're about halfway done on this puppy. So let's keep on going. Calculate the mass, that would be in grams, of 1.8 times 10 to the 24 molecules of calcium cyanide. Okay, so we're going to start off with number, units, and a formula. So that is 1.8 times 10 to the 24 molecules, MOLEC, of calcium cyanide. So calcium is Ca2+. Cyanide, because it's a group 2, cyanide is a polyatomic ion, Cn, and a 1-. Okay, so I'm going to take the bull by the horns, absolute value, flip, bring it down, and I get Ca, Cn, and the parentheses, and a 2. Draw my monorail right here, just like that. Okay, looking good. So molecules are in the numerator here. Consequently, molecules needs to be in the denominator, the same formula, Ca, Cn, parentheses 2. I'm going to go from molecules to something and then eventually to mass. So I want to end up here on the left-hand side, which is mass. And as you can see right over here are molecules. So I'm going to go from molecules to moles and then moles to mass. So molecules to moles, this tells me my units in my numerator, which is moles. So this will be mole. And that's Ca, Cn, and a parentheses and a 2. Now I'm going to figure out what the numeric values are for these. So number in front of the mole is a 1. Number in front of molecules is Avogadro's number. Number in front of the mole is a 1. Number in front of molecules is Avogadro's number, 6.022 times 10 to the 23rd. Okay. This enables me to cancel out molecules of Ca, Cn parentheses 2. All right. Cool. These are moles here in the numerator, moles here in the denominator so that the units cancel out. And then the formula CaCN parentheses 2 is going to cancel out. And I'm looking for a moles to mass. This tells me grams is in my numerator term. That's G for grams and CaCN parentheses 2. Okay, this will enable me to cancel out moles of that. Now I need to figure out what the numeric values are for this. So what's the number in front of the mole? It's a 1. Perfect. And that's right there. And then the number for the calcium cyanide is the molar mass. So here is calcium. It's 40.08. There's 1 of those. And for cyanide, there's 1 carbon times 2, and then 1 nitrogen times 2. So I'm going to take both of these. You can either sum them up and multiply by 2 or individually multiplying by 2, but those have 3 decimal places. Calcium has 2. So I'm going to have 2 decimal places in my rounded molar mass. It's going to be 92.12. Perfect. Number of significant figures. This has 2 significant figures. This has 4 significant figures. This has an infinite number of significant figures, infinite number of significant figures, and 4 significant figures. So this has 2 significant figures here. This is infinite because it's a definition that has 4, and this is a definition, so infinite, and this is from the periodic table, that's 4 significant figures. So my calculator answer will have 2 significant figures, and the correctly rounded answer is 280, no decimal, so it has 2 significant figures, grams of CaCN parentheses 2. Cool. That is number 10. We're looking good. Oh, by the way, remember you are watching The Crazy Hat Chemist. Please watch my videos on YouTube and subscribe to my channel. And yeah, I'm The Crazy Hat Chemist. So next piece of paper here, and that is starting off with number 11. So pop this up here. Here we go. Straighten that out a bit. Awesome. All right, so it says we have 1.8 liters of molecular chlorine gas at STP. What is the mass? So 1.8 liters of chlorine gas. Chlorine is one of the diatomics that I aforementioned earlier, so it's Cl2. Number, units, formula. You notice I've been doing that this whole time. Even me, as a chemistry teacher, does not stray far from that whatsoever, because it is the way to always get it right. So if these are liters in the numerator, then I will have liters in the denominator here. The same formula, Cl2. Hopefully that's good for you right there. Yeah, okay, good. So I'm going to go over here and go, I need to go to mass, and I have a volume. So I have a volume. I want to go to mass. There's no direct route. I'm going to go from volume to moles. That tells me what my numerator is for units. That's moles. Same formula, Cl2. Okay, now I'm going to look and find out what the numeric values are. So the number for the liters is 22.414. 22.414. The number for the mole, as it has always been, is a 1. That is a 1. This cancels out my units of liters and the formula of Cl2. I'm going to keep on going, and I'm trying to get to a mass. So right now I'm at moles. I want to go to mass. So whatever these units are right here in the numerator, they must be here in the denominator. That's moles, and this is Cl2. and I am going to go for the mass. So I'm going to go from moles to mass, and that will give me grams. Grams is mass, and that's Cl2. What's the number in front of the mole? It's a 1. Okay, 1 in front of the mole. And then I'm going to pull out my periodic table, and I'm going to look at chlorine on the periodic table. It's 35.453. I'm going to multiply that by 2, and then I'm going to have 3 decimal places. And so that numeric value would be 70.906. This will enable me to cancel out moles of chlorine. I'm going to look at significant figures. This has 2 significant figures, 5 significant figures, infinite number of significant figures. Definition, 1 mole equals that number. Definition, 1 mole, that's why this is infinite. 5 significant figures. So the fewest number of significant figures in this problem is 2. So I'm going to plug this into my calculator, then round this to 2 significant figures. And that will be 5.7 grams of Cl2. And there's my answer. Number, units, formula. Yes! Awesome. Okay, so next problem here. Next problem here is really a problem that you should be able to do just by canceling out units, and that's why I've incorporated it in this. It's not talking about the gas unit yet. If we're talking about the gas unit, then we can work with non-STP conditions, but we're going to calculate the density. So I'm assuming that you understand generically that density is mass over volume. Okay, and mass that we have thus far in this unit is grams for units. Excuse me. The volume that we have is liters, and those are our units here. So we're going to have something using all of this information here. But the key to this is that it's at STP. So I want to get dinitrogen pentoxide. So prefix di, that's for 2, prefix penta, that's for 5. So nitrogen oxide, dipenta. That's how I get that formula for dinitrogen pentoxide. It's a gas. Okay. And so what we're going to do is we're going to calculate the molar mass. So we're going to have grams here of N2O5. And grams is equal to what? Grams is equal to moles. Moles of N2O5. And how many moles? 1 mole, just like always, 1 mole. And the molar mass for this dinitrogen pentoxide, so I'm going to look on my periodic table. I'm going to find nitrogen. I'm going to find oxygen. They're 2 times 14.007 plus 5 times 16.00, and I'm going to round that to 2 decimal places. So that will be 108.01. That's the mass of 1 mole. That's why it's called the molar mass. Then there's another really interesting thing that we know at STP conditions. So at STP, 1 mole is equal to 22.414 liters. So we're going to actually cancel out our units here. What units do we want to cancel out? Moles of N2O5. So 1 mole of N2O5 is going to cancel out with these moles of N2O5, not the number, but just the units and formula. And this is equal to 22.414 liters of N2O5. And the units that don't cancel out are grams per liter, which is a density. So I think I'm pretty happy with that. This is an infinite number of significant figures. Infinite, this is 5, this is 5. My answer will have 5 significant figures. So that's going to equal 4.8189 grams per liter of N2O5. There is my number, units, and formula. The units are grams per liter, and the formula is N2O5. Yes, fantastic. I hope you're cruising along here. So let's go to number 13, lucky number 13. I like number 13. It's actually my favorite number. Here we go. one atom of an unknown element that is monoatomic, this is going to be critical, monoatomic, has a mass of this in grams. That's 1.7934 times 10 to the negative 23. What is the molar mass? So molar mass is grams per mole. Hopefully you remember that. I just wrote that off to the side. There we go. Grams per mole. Okay. And the identity of this element, of this unknown element, figure out what that is, and then using the periodic table and the known molar masses. So we're just going to draw ourselves a monorail right over here, and we are looking to get grams per mole. That's what we're ultimately looking for. It says in the problem that I have 1.7934 times 10 to the negative 23 grams. And why am I putting this in the numerator? Because I want units of grams in my numerator. That is why. And we don't know the element, what the element name is or the formula, so I'm just going to call it element X, but it is monoatomic. It's not diatomic. And it says one atom has this mass. So that's one atom of element X. Okay. All right. So what we need to do is we need to actually cancel out the units for atoms and eventually get to moles. So let's cruise over to this here, our map. Our map is we have atoms. We want to go to molecules. And then from molecules, we're going to go to moles. We are going to leave the numerator units untouched because they are what we want. So these are atoms. I'm going to have atoms over here of element X. From atoms, I can go to molecules. That's molecules of element X. And now it's, if I look at my flow chart, my map, it's one molecule and counted number of atoms. So it's one molecule, and I'm going to count the number of atoms here. Oh, one. So that makes that really nice and easy. So you should see that the atoms cancel out. Still have my units of grams in the numerator. That doesn't cancel out. I'm one step away from canceling out with the molecules. So I'm going to cancel out the molecules. So they need to be in the numerator in order for me to cancel out the units of molecules. It is element X, so I'll put that there. And then I need to get moles in the denominator, right? Because I want moles. So I'm going to get moles. So I'm going to go from molecules to moles. What's the number in front of the mole? It's a 1. What's the number? Mole of X, and it's a 1. And what's the number in front of the molecules? Avogadro's number when you're going back and forth between moles and molecules. So that's 6.022 times 10 to the 23rd. Awesome. And now the units that don't cancel out are grams per mole. And that will give me my molar mass of this unknown element. Okay, so I'm going to plug this into my calculator and I am going to get 10.800. The units are grams per mole, and that's of element X. And then if you look at this on the periodic table, you're going to find a molar mass that is closely approximating that, and that's right here. And that's 10.811, and that's going to be B for boron. So I'm going to say this boron. Oh my gosh, that is so exciting, isn't it? Boron. Oh, I knew you were excited about that. All right, now we're going to go for the next one here, and I'm going to try to leave up this problem number 13 here so that you can see the process here for number 14, because it is very, very similar. Okay, we have one atom of an unknown element. It's a molecule that's diatomic this time, and it has a different mass, of course. And we're going to try to identify this baby. So we're going to be doing the same thing. We are going to try to get units of grams per mole. So that's what we want. That's why we're going to put this number here, 5.887246 times 10 to the negative 23 grams. We'll call this one Y2. Why? I don't know, because. And then 2, because it's diatomic. And it says it's one atom of Y has this. Okay, and so what we're going to do is we want to keep these units of grams, but cancel out atoms. So atoms of Y and molecules of Y. So just making sure here. So it's really molecules like 2 right there. Okay, and we're looking for the atoms to cancel out here. So let's make sure that these are molecules that need to go there, but it is following the same format as number 13. I'm canceling out the atoms, and I'm going to go to molecules. So I have atoms. I want to go to molecules. It's one molecule counted number of atoms. One molecule counted number of atoms. That's 1, 2. That's a 2 right there. All right. You like that? Perfect. All right, now what we're going to do is we want to cancel out the molecules. So molecules are going to go up here of Y2, and we're going to go from molecules to what? Molecules to moles. Molecules is going to use Avogadro's number. Moles is going to use a 1. So molecules is going to use Avogadro's number, 6.022 times 10 to the 23rd. And moles of Y2, that is going to use the number 1. So now the molecules cancel out. Sweet. Okay, we're going to plug this into our calculator, and then we're going to get the following number. That is 70.90599. That's grams per mole of Y2. And Y2, what is Y2? So it's diatomic. So that means that it must be either nitrogen. Let me put all of them up here. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, or hydrogen. So which one of these has a molar mass when it's Y2? That is H2, O2, N2, Cl2, F2, Br2, I2. And the only one that this corresponds to would be Cl2, which is chlorine. Perfect. All right. Yes. Okay, another problem down. All right. Now what we're going to do is we're going to shift gears just slightly, and we are going to do another type of problem. And we are going to calculate the empirical formula of a compound. Okay, and so empirical formulas. Here we go. Empirical formulas are based on the definition, and the empirical formula is the simplest whole number mole ratio. That's what we're looking for. It's the simplest whole number mole ratio. So it says that this compound is 64.5% chlorine and the remainder of it nickel. Okay, so we're going to figure out the remainder amount, which is the nickel amount. So we're going to take our 100% minus the 64.5%, and that will equal 35.5%, and that is for the nickel. Okay? All right. So moving this up just a little bit more here. So we're going to make an assumption, and that assumption is we have 100% of the compound. If we have 100% of the compound, then we're going to assume 100 grams. Assume 100 grams. If we assume 100 grams, then our percentages will now be converted into masses. So I have 35.5 grams of nickel. Okay, and then I also have 64.5 grams of chlorine. Okay, and so I'm going to go back to our definition of empirical formula, and it's the simplest whole number mole ratio. And that definition tells you how to do this problem mathematically. So the first thing I need to do is get moles of these, and then I'm going to get a ratio of moles. So I'm going to get the molar mass of chlorine. That's 35.453 grams of Cl. Notice that this is not diatomic. This is the atom of chlorine, because I don't know how many atoms of chlorine are in the formula. So I'm just using 1. That's equal to 1 mole of chlorine. Okay. And then for nickel, I'm going to look on the periodic table, and that's 58.69 grams of nickel. And that's equal to 1 mole of nickel. That is the molar mass that's on the periodic table. So I'm going to get these two numeric values. That's 35.5 divided by the 58.69. And I'm going to get this value of 0.3 60487306185. And then this one for the chlorine is 1.8193100724.9. Okay, these values are moles. So this is moles of nickel, and this is moles of chlorine. And so I'm going to go back to our definition again. I'm going to get the simplest whole number mole ratio. So I need a ratio. So I have moles. Finally, now I'm going to get a ratio of moles. So I'm going to divide both of these to get a ratio of moles. So I need to divide by the smallest. So the smallest number of the pair here is this number. So I'm going to divide both numbers by the same small number. Same number. I'm going to divide them both by the smallest number. You are always dividing by the smallest number. Okay. And then what I'm going to do is get a numeric value. This is 1. This is an exact number. So there's 1 nickel in this formula, hopefully. And then this one will be 3.0. And I'm only looking at the 10th position. I'm hoping for a 0. And I do have a 0. So my formula is going to be Ni1 Cl3. And there's my empirical formula. That's the simplest whole number mole ratio. Okay, that's just a few more problems. And by the way, you are watching The Crazy Head Chemist. Okay, watch my videos on YouTube and give me a thumbs up, please, if you like these explanations. We're going to keep on going here. We have 1, 2, 3, 4, 5, I think 5 more problems left to do here. So we're getting closer to the end. Going to be happy about that. Okay, we're going to calculate the empirical formula of a compound if the percent composition is 56.58% potassium, 8.68% carbon, and the remainder mass is oxygen. So what we're going to do is I'm going to do this right up at the top, since this one is going to be lengthy, 100 minus the sum of 56.58 and 8.68. And that will be the remainder, which is oxygen, and that is 34.74% oxygen. Okay, so that's how I get the amount of oxygen. All right, so we're going to start off with the potassium, the carbon, and then the oxygen. So the potassium amount, again, we are going to assume 100, since we have 100%, we're going to assume 100 grams. Therefore, our percentages are now grams. 56.58 grams of potassium. And we are going to get the simplest whole number mole ratio. So the first thing that we need to do is determine the number of moles. I'm going to look on my periodic table, find the molar mass for potassium. That's 39.10. That's grams of potassium. And then that's equal to 1 mole of the same potassium. I'm going to do a similar thing here for the carbon. So I have 8.68 grams of carbon. And I'm going to look on my periodic table. I'm going to find the molar mass of carbon, 12.011 grams of carbon. And there is 1 mole that is equal to for carbon. And then I'm going to get the oxygen, and that is the 34.74 grams of oxygen. And that is 16.00 grams of oxygen, and that's 1 mole of oxygen. Awesome. Now we're going to get numeric values for all of these. Okay, so for the potassium, it's 1.447058 2353. For the carbon, it is 0.72267085022. And the oxygen is 2.17125. So now I have mole values of each of my elements. So the empirical formula is the simplest whole number mole ratio. So I'm going to divide each of these by the smallest number. So I'm going to divide them all by this same small number, which is that for the carbon. I'm going to divide them all by the smallest number. That is the key to this. 7226708850022. Okay, so dividing them all by the smallest number. Okay, that will get me this one. This is an exact number. This is 2.0. That's really nice. And this one is 3.0. That's nice as well. I am looking for, in the 10th position, the number to be either a, hopefully a 0. If it's not a 0, it should be a 1, and then I go and chop it off, or a 9, and I can add 1 to the preceding digit. So how many potassiums? 2. How many carbons? 1. How many oxygens? 3. And there is my empirical formula, simplest whole number mole ratio. And you should actually know the name of this. So before I come up with the name, I'm hoping that you're going to come up with the name of this. And that is potassium carbonate. Cool. Potassium carbonate. Here we go, potassium carbonate. All right, cool. All right, we are going to cruise over to number 17. Here we go, number 17. Number 17, it says that we have, we're going to determine the empirical formula yet again, and the percent composition is 51.9% chromium, and the remainder is sulfur. So 100 minus 51.9, that will equal 48.1. That is the percent of sulfur. We're going to say that we have 100%. Therefore, we have 100 grams. That's our assumption to make the math work out nicely. So now what we're going to do is we're going to take our 51.9 grams of chromium, and we're going to convert that into moles. And then we're going to take the 48.1 grams of sulfur and convert that into moles. Okay, so I'm going to look on my periodic table, find the molar mass for chromium. That's 52.00 grams of chromium. That's equal to 1 mole chromium. And then the molar mass of sulfur is 32.06 grams sulfur. That's equal to 1 mole sulfur. Okay, moving this up just slightly here. All right, so I'm going to get numeric values for this one. That is for the chromium, it's 0.9980769. 23077, and for the sulfur it is 1.50031191516. And like I've been doing on all of these, I'm going to divide both of these by the smallest number. So now I have mole values, but I need the simplest whole number mole ratio. So I'm looking for a ratio of moles. So I'm going to divide this one by the same number. Divide this one by the smallest number. And then I'm going to get values from this. And this one will be 1. That's exactly a 1. And this one is 1.5. So now here we have a bit of a dilemma here. And that dilemma is as follows. This in the 10th position is not a 0, it's not a 1, and it's not a 9. So what we're going to do is we're going to take the value 0.5, and we're going to take the reciprocal of 0.5. So that is 1 over that. That number is equal to 2. This is my multiplying factor. So whatever is the decimal value, you take that decimal value, take the reciprocal of that, and that is your multiplying factor. So I'm going to multiply this by 2. That will give me a whole number of 3.0. If I multiply this by 2, I need to also multiply this one by 2 here as well, and any other elements that are within this formula, and that will be 2 exactly on this one. So the formula of this is Cr2S3. And that hopefully should make sense. This is chromic sulfide, or chromium Roman numeral 3 sulfide. That's the name of this compound. So chromic sulfide, or chromium Roman numeral 3 sulfide. Cool. That's pretty awesome, I think. I like that a lot. All right, so we are going to keep on going here. So we're going to go on to the next one. Here's our next one. And it says determine the empirical and molecular formula. So we got 2 tasks here, but they are very closely tied together. Okay. If the percent composition has been determined to be 9.15% hydrogen, 54.53% carbon, and the remainder oxygen. So just like before, we're going to take our 100% minus 9.15 minus the 54.53, and that will give us our value for the amount of oxygen, which is 36.32. Okay, so I'm going to, whoops, just off table there, just a little bit. There we go. So I'm going to do the same thing that we did on the last problem. We're first going to get the empirical formula, and then we will work about the molecular formula. So again, the empirical formula is the simplest whole number mole ratio. So let's work on that first. So I have 9.15 grams of hydrogen, and we're going to convert this into moles. So that's 1.0079 grams hydrogen, and that's 1 mole of hydrogen. And then I have, what do we have? We have carbon, okay? And so that is 54.53 grams carbon, and that's 12.011 grams carbon. That's 1 mole of carbon. And then I have my oxygen at 36.32 grams of oxygen, and that's 16.00 grams oxygen. That's equal to 1 mole of oxygen. Okay. Now, all these values are here. This is 9.07828.157. You can actually have more numbers on there. I've been giving you an immense number of numbers, but I'm going to round these a little bit more. 4.540000499, and then 2.27. So these are all the mole values. So again, our rule for these problems is the simplest whole number mole ratio. So that means I need to divide all of these by the same smallest number, which in this case is really nice because it's 2.27, 2.27, 2.27, 2.27. And I am going to get the following numbers from that division. I'm going to get 3.9, which will be 4. And then I will get 2.0, so that's good. And then this one is exactly 1. Okay, so my empirical formula, the simplest whole number mole ratio, is going to be, and I don't know if you remember this, but when we were doing combustion reactions, we had the carbons first, then the hydrogens, then the oxygen. So I'm going to put that in that order because that's the way you should have it. Carbons, how many? Carbons, 2. Then hydrogens, how many? Hydrogens, 4. Oxygens, 1. And I don't write ones. So this is the empirical. It's the empirical formula. Okay. Now, there's a ratio between the empirical and the molecular formula, and that is going to be this right here. So N is going to be my multiplying factor, and it's all about me. That's the molecular over the empirical formula. Okay, so it says in the problem that the molecular formula's molar mass is 132.16. 132.16 grams per mole. Now what we're going to do is calculate the empirical formula's molar mass using the periodic table. And that is going to be 44.05. So I'm going to divide by the empirical formula's molar mass of 44.05. Then I'm going to take this molecular formula's molar mass divided by the empirical formula's molar mass. Do you see it's all about me? You know, you have to be self-centered on some of these problems at least, because ME, that's molecular over empirical. Molecular's molar mass over empirical's molar mass. And this will always be a whole number, 3.0. So it could be a 2.0, a 1.0, a 5.0, whatever it is, it will always be a whole number. So now what we're going to do is we are going to take what we have for the empirical formula and multiply it by this multiplying factor. So C2H4O, we're going to multiply it by this 3. So we're going to take 3. And now we're going to distribute this 3 over all the terms. So this will be our molecular formula. So 3 times 2, that's 6. So it's C6. Then it's 3 times 4, that's 12. And 3 times 1, that's 3. So the molecular formula is C6H12O3, whereas the empirical formula is C2H4O. So the empirical formula is the simplest whole number mole ratio. The molecular formula is a whole number multiple of the empirical formula. Fantastic. All right, we're going to peel this away. And oh, by the way, you are watching The Crazy Hat Chemist. Please subscribe to my YouTube channels and my YouTube channel and give me a thumbs up on this video. We are almost done. We got 2 more problems to do. So hang on to your hats, so to speak. Okay, here we go. From a combustion analysis, so this is our next one here. We have 53.29% oxygen, 40.00% carbon, and the remainder is hydrogen. So again, what we're going to do here is what we've done, similar problems. We're going to take 100% minus 53.29 plus the 40.00. That will give me 6.71 grams of hydrogen, or percent of hydrogen. We're going to determine the empirical and then the molecular formula, knowing that the molecular formula's molar mass is 180.12. All right, let's get banging on this one. So we have 53.29 grams of oxygen. We're going to convert this to moles of oxygen. That's 16.00 grams of oxygen, 1 mole of oxygen. Then we have 40.00 grams of carbon, and that will be 12.011 grams of carbon, 1 mole of carbon. And then we have 6.71 grams of hydrogen. That will be 1.0079 grams of hydrogen, 1 mole of hydrogen. And again, what we're trying to do is get the simplest whole number mole ratio to get the empirical formula. Okay, and so the numeric values that come of this are 3.330625 and 3.330280 and 6.657406.4. Okay. We need to divide all of these. So we have moles, and then we need to get mole ratio. So we're going to divide all of them by the smallest mole value, which happens to be, well, this one right here, 3.330280.5. 3.3302805. And you notice that this one for the oxygen is really close to that of the carbon, so these numbers will be pretty much the same. 3.3302805. Okay, perfect. This is going to be a 1.0. This is my exact number of 1, and this is 1.9. I'm going to add a tenth to that, and I'm going to get 2.0. Okay, so now what we have is the empirical formula of this, and we're going to write this in the correct order. That's carbons, hydrogens, and oxygens. How many carbons? 1, 1. How many hydrogens? 2. How many oxygens? 1. So this is empirical. That's my empirical formula. And since we're trying to get the molecular formula, oh my gosh, you didn't just see what I wrote there, huh? I need to zoom this out just a little bit. I apologize. So I'm going to try that again. Okay, so we're going to write this carbons, hydrogens, and oxygens. And how many carbons? 1, 1. How many hydrogens? 2, 2. How many oxygens? 1, 1. This is my empirical formula. Okay, now we're going to get the molecular formula. So it's N is equal to molecular over empirical. Okay, and we're going to get the molecular formula's molar mass, that's 180.12, divided by the empirical formula's molar mass. So you have to calculate this using your periodic table, and that's 30.03. This is grams per mole. So 30.03. So what we're going to do is divide these and get our N value for this, and our N value comes out at 5.9, which would round to 6.0 if I add a tenth. So that means my multiplying factor is 6. So I'm going to multiply this by 6, and that will get me my molecular formula. So my molecular formula is right here. So it's C6H12. O6. So C6H12O6. And this is the molecular. And you should recognize this as sugar. Okay. Sugar, we are almost done. Okay, here we go. One more problem. I think we might be able to accomplish this. Here we go. One more problem. Sliding this up. Slide me some chemistry problems. All right. It says determine the molecular formula of the sweetener NutraSweet. Its molar mass is known right there, 294.30 grams per mole. The percent composition of NutraSweet is carbon, hydrogen, nitrogen, remainder oxygen. Okay, so let's see if we can do this here. Our carbon is 57.14 grams of carbon. And we're going to convert this into moles. So that's 12.011 grams of carbon, 1 mole carbon. And then we have 6.16 grams of hydrogen. Going to convert that to moles of hydrogen, 1.0079 grams hydrogen. Then we have 9.52 grams of nitrogen. That's 1 mole of nitrogen and 14.007 grams of nitrogen. And we're going to move this up so that we got all this on our page. Okay, fantastic. And then you're going to take 57.14 plus 6.16 plus 9.52 and subtract that from that sum from 100. You're going to get 27.18 grams of oxygen. And that's 16.00 grams of oxygen. That's the molar mass, 1 mole of oxygen. Okay, all right, fantastic. Here we go. Still with me, don't go away. Last problem, you can make it. All right, So we're going to get numeric values for all of these, and this is a 4.75, 7305. This one is 6.111717. This one here is 0.679660, and this one here is 1.69875. So simplest whole number mole ratio. So what we're going to do is we're going to divide all of these by the smallest mole value, which is obviously here for the nitrogen. So that's 0.679660. 679660, 679660, 679660. And that will give us the following values of 6.9, that will round to 7. And then this one is 8.9, that will round to 9. This one is exactly 1. This one is 2.5. Ah, shucks. There we go again. Okay, so notice that this is the 0.9, 0.9. I'm good. I can add a 10. This one is 0.5. So I'm going to take the reciprocal of 0.5. So 1 over, let me move this up, 1 over 0.5, that's equal to 2. So that means I'm going to multiply this by 2, multiply this by 2, multiply this by 2, multiply this by 2. I'm going to get 14, 18, 2, and 5. So that will give us my empirical formula. And so I've written these in the order of which they should be. So carbons is 14, hydrogens are 18, and nitrogens are 2, and oxygens are 5. This is the empirical. Okay, there's the empirical formula of NutraSweet. Now, we need to get the molecular formula of NutraSweet, molecular formula of NutraSweet. So we need to get the molar mass of this empirical formula, and that molar mass is 294.31. Wait a second. Wait, just hold the boat. N is equal to molecular over empirical, right? So the molar mass that was given here for the molecular formula is 294.30. The molar mass that's calculated for the empirical formula is 294.31. That is a 1. That means the empirical and molecular are the same. So the empirical and the molecular formula is the same. Oh my goodness. That is fantastic. So I hope that worked out well for you. I'm going to place it right up here because this is really the key to everything here. And this right here flow chart is so very, very important. Okay. So mass to moles, moles to molecules, molecules to atoms, then atoms to molecules, molecules to moles, moles to mass, and then we got moles to volume, and eventually we're going to keep on going in stoichiometry, and we're going to go up here. We haven't gone up there yet. I hope you enjoyed this video. I am the Crazy Hat Chemist, and please watch my videos, subscribe to my YouTube channel, and I'd greatly appreciate that. Have a good evening. Talk to you later. Bye for now.